Hello, everyone. Welcome to the Question Show. Your questions, my answers, as always, wherever you are, across my channel, or really anywhere in the universe. If a question pops in your brain, just write it down, or think it, or dream it, or email it. I'll gather them up, and I will answer them here. Now, I record this show live every Monday at 5 p.m. Pacific time, whether that's daylight savings time or standard time. It's always 5 o'clock. Somewhere. So why don't you come and join us live, and you can ask your questions and ask follow-up questions and chat with the rest of the audience. It's a lot of fun. So remember, every Monday at 5 p.m. and I will put the next live event somewhere around here on my channel so you can give yourself a reminder. But if you subscribe and then click the little bell, then you'll get a reminder, and it's much longer, a lot more fun than just the very quick question show that you see. So definitely come and hang out. All right, let's get into this week's questions. Jamie Venables, will it ever be possible to gather enough hydrogen and helium to artificially create a new star? So I guess this is kind of a follow-on question to the episode we did a few back about gathering the hydrogen off of Jupiter. And so sort of taking it to the next logical extreme, could we make our own star? And I think the thing that's really important is that stars are bad as a source of energy. Stars are wasteful, inefficient. When you take an object, it's really hard to kind of wrap your brain around the size of the sun. It's more than 1 million kilometers across. It's an incomprehensible amount of hydrogen. It's more than 99% of all of the mass in the solar system, and it's in this ball, and only in the middle is it actually fusing hydrogen into helium in the core. There's a big section around it where it's just not hot enough and high pressure enough for it to be able to work. And so the sun will die having only used up a portion of the hydrogen that it had available. So stars, if you want to power your civilization, you don't want to build a star. Stars are the worst. What you want to do is you want to build a fusion engine. You want to build fusion reactors and then run those. And so you want to, ideally, we want to destroy the sun. We want to siphon away all of its hydrogen before it wastes it. And we want to take that hydrogen fuel, store it in blobs, maybe Jupiter-sized gas planets, or maybe smaller, so that they won't get rid of their hydrogen, and then mine it nicely and run them in our fusion reactors. And if we do that, then they would last for trillions, quadrillions of years. So one of the viewers, David Sims, did a calculation that if you were able to turn Jupiter into fusion reactors, it would last you longer than the stars have all gone out. And so just imagine, we just take all the stars, we take the sun, we take all of the gas giant planets, and we're efficient with the fuel. We could make it last for a very long time. And then when you think about the fact that hydrogen is the most plentiful element in the universe, we've got a whole galaxy waiting for us to harvest and turn into our fusion reactors. And then we'll use them much more efficiently than those stupid stars. I mean, the stars, they're just beaming all this energy in all directions. What good is that? So, then could we gather up hydrogen from the interstellar medium? I guess so. But we want to go to the big clouds of cold molecular hydrogen. We want to take it from the stars and siphon them away. We want to dismantle gas giant planets. That's what we want to do. Gravel pit. I feel like we've reached a ceiling in our space ambitions. We've sent probes all over the solar system, and we've put humans on the moon. But the real question now is, what should we do if we really want outer space long term? Do we really want humankind to colonize another Earth or not? That mission will take our full focus, and time is not our friend. We should build telescopes capable of finding an Earth analog, and then we should build O'Neill cylinders that we can take us there. I think human beings have explored every nook and cranny of planet Earth, and it is just what we do. And maybe this is part of just what life does. Life is always looking to find places without competition so that it can exploit the resources. And that's why every nook and cranny of the entire planet Earth has been exploited. That's why human beings have gone. We're looking for open pastures. We're looking for places that nobody has shown up before so that we can exploit the resources. And it feels logical for us to take that almost evolutionary drive and then take it to the next level and say, how will we expand and extend that to the rest of the solar system? And then we think, well, we're going to have colonies across the moon and Mars and the asteroid belt and Titan and Pluto, and we're just going to have people living across the entire solar system. But we did not evolve for those environments. We evolved for this environment. Our ability to just survive and stand out under the sky and breathe and not die begins and ends with the surface of planet Earth. So I think that we're going to have a hard time justifying trying to extend the human experiment to other places around the solar system. And in fact, we're even in this point now where it looks like our population on planet Earth is going to peak within the next few decades. In many nations, populations are going down. We're not going to run out of space on planet Earth. We're not going to run out of resources on planet Earth. And so I think that we will have some really interesting science colonies or some science missions on the moon, on Mars, asteroids, maybe Titan, why not? And then as our technology gets a lot better, we can start to trivialize some of the really horrible things about space, where we're living in maybe some space stations for fun or for some interesting experiments or as a way to test out different ideas. But at the end of the day, it's really hard to pay out of pocket all of the stuff that Earth is doing for us for free. And it's just not going to make sense. So I think that we are in this point of the human story where it feels like we're running out of room here on planet Earth. And it feels like the next thing for us to do, to put our eggs in multiple baskets, to go to Mars, to colonize, and then consider how we're going to go to other star systems. But I can't get across. I feel like I just can't get across how awful those places are across the solar system and how far away and difficult it's going to be to go to other star systems just with our robots, not even with human beings. Like, for us to, like, if we just keep growing in our technology and our energy expenditure, yeah, maybe in 200 years we'll be much more of a solar system spanning civilization, and maybe in 1,000 years or so, we'll have the technology to be able to go to other star systems, which is it's a blink of the eye in the history of humanity. But that's just going to be our robots. And we will probably never send our meat bodies to other star systems because it's just so far away. And Earth is so good. We will never find a place that is better for us than planet Earth. And we're living on it right now. So I do agree with you that I think we've reached a ceiling in our exploration in terms of in our colonization, but not in our exploration. There is every single asteroid, every moon, every planet, every comet, every Oort cloud object, the sun, all the Trojans. There are so many places to explore and understand and discover across the solar system, and that's going to keep us busy for centuries. So we're going to explore. I don't think we're going to live. Josh Russell, how far on the Kardashev scale would be possible for it's no longer possible due to the heat death of the universe? Would a civilization along that progression have to be able to counteract or inhibit that barrier as part of its development? Is there realistically the time to get very far on the scale? So, like, the inevitable future of the universe is the heat death. And this is this idea that all useful differences in temperature will have evened out. And so right now we have these really hot stars and really cold space, and the stars are radiating heat that we can gather as solar energy and do work with them. But eventually the stars will die, and their dead embers will cool down to the background temperature of the universe. And the all of the gas that's available for use will have been sucked up into a star, and then the star will have died, or they'll be sucked up into black holes, and the black holes will evaporate, and everything will be the background temperature of the universe. Just a teeny tiny little bit above absolute zero. And that is the heat death. And you can just no longer do any work. No. And that's a long time, like a 1 followed by 100 zeros. So it's a very long way. And that's probably one of the laws of the universe. That there is no way to escape that final, like we may be able to avoid the sun heating up the earth by shifting the position of the earth. And we may be able to avoid the death of the sun by, as I said, stripping the sun down, storing it in blobs of hydrogen, using it to burn our fusion reactors for quadrillions, quintillions of years. And then we may be able to avoid the death of all the stars in the Milky Way by going out, grabbing them all, tearing them all apart, turning them into blobs of hydrogen, batteries for our fusion reactors. But eventually, we will run through all of that fuel. Maybe we'll figure out a way to harness power from black holes by using the Penrose process, where we drop stuff into the black hole and harvest the kinetic energy as things are falling back out of it or thrown back out of it. But eventually, the black holes will no longer be rotating. The hydrogen will have all been used up and burned in our fusion reactors. We will have run out of every single possible way to exploit any kind of energy difference to do work in this universe. And, maybe you can, if you're a computer entity, you can slow down your clock speed so that you could harvest the energy from the cosmic microwave background radiation, and maybe you can live in the really close to the event horizon of a supermassive black hole where relativistic time dilation works in your favor to last even longer. But eventually even those will run out, and then that will be that, and there will be nothing else that we can do. And like what you're saying is like, could we figure out a way to not suffer the heat death of the universe, not be finally wrapped up by the heat death of the universe? But that's literally the definition. Like, the heat death of the universe happens when we run out of ways, when we're all out of tricks. We got nothing else we can do. And maybe we're going to be in one little pocket, and our pocket of the universe will be the last place to suffer the heat death. But it'll happen. And then there will be nothing else that we can do. Now, obviously, you can, maybe we'll open up a portal to an alternate universe, and maybe we'll realize a way to come up with infinite energy, and maybe we'll figure out a way to harness vacuum energy. Although with vacuum energy, we use all that up, and we're back to the heat death problem. But maybe we reach the heat death of the multiverse. Like, in the end, entropy wins and we lose. So, but it's an incomprehensible amount of time from now. So don't worry about it. Enjoy your life. Have fun. Eat ice cream. Brian Sparks. Here, Fraser, on a gas giant planet such as Jupiter, how do they determine where the surface starts and the atmosphere begins? There isn't really a surface on a gas giant. Like, if you were to take Jupiter and slice it open and look inside its interior, you would have down at the core a rocky-ish, more solid elements. Some of the heavier elements would have sunk down to the middle, a couple of Earth's worth of mass. But then surrounding that, you've got hydrogen and helium compressed to the point that it is like metal at tens of thousands. I think it's like 80,000 Kelvin inside Jupiter. And then as you move up, the temperatures come down, the pressures come down, and so now it acts like a liquid, like a goo, and so on and so forth. And it's only in the top couple of 100 kilometers that you switch from various amounts of hydrogen and helium under intense pressure to the atmosphere. And in this case, now you've got, ammonias, methane, various other gases that are surrounding Jupiter. And that's where all of the clouds and the storms and stuff that we can see. So what is the surface of something like that? You could say that the surface of Jupiter is the cloud tops. That's because beyond that is space. Sort of in the same way that the surface of the sun is like where the top of the sun is, and as opposed to my rice just finished. All right. So what is the surface? What do you mean by the surface of Jupiter? I mean, is it the surface is the cloud tops? Is the surface where the atmospheric part begins? So there's no real answer to that, and that's because Jupiter is a gas giant. It's made of hydrogen and helium in various levels of pressure and density and temperature, and it's not an easy question to answer. Double B99. Hey Fraser, I have a question. How much thrust do you need to escape the surface of Venus, and how much different is rocket propulsion there compared to Earth? So Venus is about the same size and about the same mass as the Earth, like within 10% of Earth. And the escape velocity of Venus is 8.87 meters per second squared. And you can compare that with Earth, which is 9.8 meters per second squared. I'm sure you've done those calculations in physics class. So the surface gravity of Venus is roughly the same as Earth. It's like, you could launch a Falcon 9 off the surface of Venus and you could carry like a little more payload, or you could go to a little bit of a higher orbit than you could on Earth. But just imagine you're just going to be using pretty much exactly the same rockets and technology. However, the conditions, like that was if Venus was like Earth and had the same kind of atmosphere and temperature and so on. But Venus has a pressure that is incredibly more dense than Earth. It's got temperatures that would melt many of the parts of the rocket. So you're going to have to deal with that. And when rockets fly, they partly are going to get to essentially to escape the gravity of the planet, but also they have to aerodynamically move through the atmosphere of Earth. And as they get higher and higher and higher, it's more about just the thrust carrying them to the escape velocity away from the gravity of the planet. But in the sort of near term, a lot of it is about the amount of atmosphere, because they're going so fast, right? A rocket is going thousands of kilometers per hour, and it is trying to push through the atmosphere of the Earth. And so that's why rockets are shaped like rockets. The pressure on Venus is like 90 times the pressure of Earth. And so it's going to be like trying to go thousands of kilometers per hour through molasses, I think it's like the surface of Venus has the same pressure as if you're 1 kilometer under the water on Earth. So imagine launching a rocket trying to hit thousands of kilometers per hour through that kind of density. So rocketry just wouldn't work off the surface of Venus. Maybe you could launch a balloon and you could get up above most of the atmosphere and then launch from your balloon, but to launch from the surface is just not going to work. More questions in a second, but first I'd like to thank our patrons: Kangarang, James Burke, William P. Wortman, Timothy Staniland, Michael W., and the rest of our 824 patrons for their generous support. Want our videos early with no ads? Join our community at patreon.com/universetoday. Leo Twana, what are the chances that we find life in the solar system? We have no idea. Like the chances are somewhere between 0% and 100%. There are places we can look, and we know that wherever there is on planet Earth, life seems to find every nook and cranny. Wherever there's water, life finds a way. We know there's places with liquid water across the solar system, probably on Mars, under the ice on Europa and Enceladus, Pluto even. So there's a lot of really interesting places to search for life, but we don't know if life has been able to show up independently, or if we're somehow connected, if meteorites have delivered life back and forth. So I put the chances somewhere between 0% and 100%. Somewhere in there. Let's find out. Verstovsek. What's the deal with the huge spikes in the James Webb picture of a star used for calibration of the mirrors? Why? We actually covered this on Universe Today. We did an article. I saw a lot of people asking this question about the diffraction spikes on the star picture, the calibration image taken by James Webb. And so Matt, I think, wrote an article about this. And you see this with a lot of telescopes, and you see this with even the Hubble Space Telescope. And sort of two pieces that come into play that cause those kinds of images. So the first thing is that the star is overexposed. If you gather the light for longer and longer and longer of some object, then it's gonna fill up the portion of the sensor and start to bleed over into other areas. And so that star was overexposed. And what's kind of incredible, I'm gonna sort of rabbit hole for 1 second, but like when you look at that picture and you see that star, it's great. It's a star. It's a star that's like 11th magnitude. If you had a small telescope or a pair of binoculars, you could probably find that star. But the part that's amazing is all these little faint, dim galaxies in the background. And astronomers have been looking and have identified a bunch of them, but some of them have never been seen before because we're seeing them in these wavelengths of light that other telescopes just don't do. And so it's like in a calibration image, James Webb did a Hubble deep field. And in fact, this is what James Webb will be able to do. It will Hubble deep field all day, every day. It can, just at the drop of a hat, deep field anywhere it wants to look. And just wait till James Webb deep fields. It's going to be just sick. It's going to be amazing. So, me and like a lot of astronomers, when they saw that picture and they saw those little galaxies in an area that there shouldn't have been anything there, it's absolutely incredible. And it's just a taste of what's coming. So why are we seeing those spikes? So like there's two parts to this. So one is that when you have a telescope that is a reflector, there are parts that are holding up the secondary mirror, and Hubble has it, James Webb has it, reflector telescopes all have this. And these spikes, as the light is coming past these spikes, it kind of goes around it and causes a bit of diffraction in the image as it's being gathered up. And in many cases, you can actually, like if you have like a reflecting telescope, you can unfocus the telescope and you can actually see the secondary mirror and the arms that are holding the secondary mirror. So that's part of the issue. But the other part of the issue is literally it's just the shape of the hexagonal elements. If you notice, they kind of match. It kind of looks like one of the junctions between the hexagonal elements. And it's the same thing. You get this diffraction off of where these hexagonal elements of the telescope are coming together. And this is something that was totally predicted by the James Webb people. You can go and look at their technical documents and they show you the diffraction spike that they're expecting. And there it was. And they're still going to be fine-tuning their image and their optics and using this to sort of do an even better job. And they're not going to be doing an overexposure of a single star to a ridiculous amount. They're going to be looking at much fainter objects, and so you're not going to see these same kinds of diffractions. So this was sort of partly just to test to make sure that they're getting the optics and the focus right. And a lot of times you'll see these kinds of artifacts in a lot of images taken by telescopes. You probably just never notice them. But if you go back and look at pictures taken by a Hubble Space Telescope, you'll see tons of these image spikes. So it's a very common thing. Cujo and friends, do you think we'll ever have the technology to send a probe into a black hole and receive data? No. The problem with black holes is that nothing, not even light, can escape them. So if you send your probe in, then it can't send its data back out. And those are the laws of physics as we understand them. So do the laws of physics not work as we understand them? Maybe. Will we figure out a way to defy the laws of physics as we understand them today and come up with a new way? Maybe. But don't count on it, but don't rule it out. We'll have to find out and see what happens. But no, unfortunately, the problem with a region that absorbs all matter and energy that falls into it is you can't get any energy out, even a signal that tells you what's going on inside of it. There might be some ways that we can learn about what's going on inside black holes by examining the event horizon, but there's no way for us to get any information from beyond the event horizon. Emmanuel Farnese. How long do we need to wait before a laser sail will bring us to Mars and beyond? Can we build a reactor to power the laser on board the spaceship itself? I'll tackle the second part of your question first, which is, can you put a laser onto the spacecraft to power the spacecraft? And the answer is no. It's like putting a fan on your sailboat. The laser sitting on your spaceship is going to be shooting at your laser sail, and it's going to be getting, as the laser fires, this is something people maybe don't realize, but when you're emitting photons, you're actually getting a thrust from those photons. It's called a photonic engine, and it's an idea for a spacecraft. And then at the same time, the photons are being captured by the sail, and the forces balance out. You have to have the laser outside of your spacecraft to be able to send it. Can we use it to go to Mars? Yeah. And in fact, if you listen to some of the interviews that I've done with some people, it seems ridiculous to me that we're trying to figure out how to use lasers to send spacecraft to Alpha Centauri. I get it. We want to go to another star. But we could use the same technology here in the solar system so much easier, lower power lasers, less complicated materials, much shorter turnaround time. Let's send spacecraft to thousands of targets here in the solar system. Solar laser sails to thousands of targets here in the solar system and learn about every single asteroid, comet, or cloud object, Kuiper Belt object, moon, everything. There are so many places that we don't have close-up pictures of yet. And yet if we could build 1,000 of these little things and zap them off towards various destinations, we'll learn how to use this technology. And once we've mastered that, then we can consider going to Alpha Centauri. But I guess it's just not as cool that you're sending a laser sail to some binary asteroid in the asteroid belt as opposed to sending a spacecraft to the nearest star system. So yeah, this technology ideally will have been tested here in the solar system significantly. Yusuf Ahmed, do you really believe that humans will survive beyond a few 100,000 more years? That's highly unlikely in my opinion. We'll destroy our planet and our species by then. Forget Mars, etc. Obviously, we're not going to survive to the heat death of the universe. All the species that have ever lived on planet Earth have gone extinct, and we are a species. And it is almost certain that we will go extinct, and probably within the next 100,000 years or so. People have done the math on this. So, but it's sort of the same thing. Every one of us thinks that we're going to live forever and that we're going to be able to get a robot body and be able to outlive the death that haunts us all. And yet everybody dies. And every species dies. And eventually every planet dies. And every star dies. And I guess every universe dies. So it's wishful thinking. And what's wrong with that? Let us wishfully think. Let us hope for a better future. Let us try to come together, work together, create and build things, have enthusiasm and ambition and optimism for a better future, and not be cynical and pessimistic and just wait for the inevitable death that haunts us all. Man, what a bummer. So yeah, obviously it's all wishful thinking, but good. Let's be wishful. Let's think and have fun. So, a very little part of me thinks that humanity will outlive the death of the earth or the death of the sun, right? I don't think we'll get past the AI singularity, which is a few decades away. Or I have my doubts that we'll get the control problem, that we'll figure out a way to control our artificial intelligence. Or we'll survive some idiot with a baby's first biolab making designer diseases in their garage or something. But we're optimistic species. And again, that's probably evolution, that we must survive, that we survive no matter what. We try to survive no matter what. So, yeah, like obviously, man. Of course. Odysseus. How well is JWST equipped to handle solar flares or other things like bursts of radiation or EMPs? I don't think James Webb is really designed to handle an EMP. Like, if someone goes out and sends a nuclear weapon close to James Webb and detonates it, I don't think they built that into the design specifications. But in terms of being able to handle the kind of regular nonsense that the sun is throwing out, yeah, it's designed to handle a certain amount of reasonable solar flares, coronal mass ejections, things like that. All like a lot of the times, the kinds of computers, the kinds of electronics that are sent to space are older. And partly that's because they're tried and true. They've been to space many times and the scientists know they can trust them. But also they're not as finicky. The size of the wires inside, the size of the chipset is bigger nanometers. And that gives you a little more sort of ruggedness, space hardiness. And so obviously this is the environment that JWST was expected to work in, and it has a lifespan of about 10 years, and the designers considered the environment and the lifespan and built it to be able to handle a reasonable amount of space weather to survive that length of time. When a spacecraft is called upon to do something more extreme, like say get really close to Jupiter, which is an even more lethal radiation environment, then they have to harden it even more or shorten its lifespan. So scientists are very well aware of the environment in space, and they just design their spacecraft to handle what it's expected to deal with during its lifetime, during its mission. And then anything that, if it survives longer, that's a bonus. And then maybe they, with missions to Jupiter, they start to give them more extreme jobs because they keep seeming to survive. So who knows? 10 years, James Webb, and then it kind of runs out of fuel, and then you don't have to worry about it anymore. Tau Ceti. If red dwarfs have lifetimes of hundreds of billions to trillions of years, does that mean that some of the first stars of the universe are still alive as these stars? Absolutely. Now, the very first stars are thought to be much different than the kinds of stars that we see today. Like the first stars were, they call them the population 3 stars, and they were made purely out of primordial hydrogen and helium and some other elements left over from the Big Bang. As soon as the universe cooled down and light could escape, these blobs, giant blobs of hydrogen came together and formed the first stars. And we have no direct evidence of these stars. They are too faint, they're too far away. Even James Webb won't be able to detect these first stars. We need a super James Webb to be able to detect the first stars. And that's reason enough, right? Like let's make the next telescope to be able to detect those first stars. But after that came the next generation of stars. Those first stars exploded as supernova. They seeded surrounding hydrogen and helium, and they created the next generation of stars. And these second generation stars, some of them are still alive today. We see them. Some of them are larger stars, but many of them are going to be these red dwarfs because the red dwarfs last for so long. And then some of the second generation stars, the big ones, exploded and they created the third generation stars. And our sun is one of these third generation stars, the remnants of an explosion from the remnants of an explosion. But there are absolutely some of those stars left over from that second generation. And it's cool. Like when astronomers try to understand, say, a population of stars, they will look at a globular cluster. And in a globular cluster, there are no young stars. And they know how old the cluster is by looking at the age of the stars that are in it, looking for the masses of these stars. And so they don't see any big, white, hot, blue stars. They don't see a lot of bigger main sequence stars than our own sun. They see the older stars, the smaller stars, the red dwarfs, the K dwarfs, G dwarfs like our own sun, and smaller, because all of the stars that were bigger and hotter have already died, and they use it as a way to figure out how old the clusters are. So yeah, absolutely, these stars are everywhere all around us, and many more will be forming into the future. but all the ones that are around us right now will live for billions and even trillions of years. Thanks everyone for asking all of your questions. That was super cool. I really appreciate it. Thanks everyone who asked questions both in the YouTube comments, but also everyone who showed up live and asked your questions and asked follow-up questions. It was a lot of fun. So if you want to join the live show, we do this every Monday at 5 p.m. Pacific time. You should come and join us. Subscribe to the channel, put a little notification bell, and you get a reminder when we're online. And then you can just show up and hang out with us. All right, we'll see you next week. If you want a single comprehensive resource for space news, you want to subscribe to my weekly email newsletter. Every Friday, I send out a magazine of space news with dozens of stories, pictures, brief highlights, and links so you can find out more. Go to universetoday.com/newsletter to sign up. It's totally free. Did you know that all my videos are also available in a handy audio podcast format so that you can have the latest episodes as well as special bonus material like interviews with me show up on your audio device? Go to universetoday.com/audio or search for Universe Today on iTunes, Spotify, or wherever you get your podcasts. And I'll put a link in the show notes. Thanks to all the moderators, and a special thanks, as always, to Chad Weber and Nancy Graziano.